Bayesian analysis is a statistical paradigm that answers research questions about unknown parameters using probability statements. Bayes' theorem incorporates initial estimates and information about the accuracy of the sources and allows the revision of estimates based on new information. There are many ways of getting probability data which can be based on management's experience and intuition, historical data, and computed from other data using Bayes' theorem. In the Thompson lumber case, we use these four conditional probabilities: the favorable market and the unfavorable market where survey results are positive, and the favorable market and the unfavorable market where the survey results are negative. But how were these calculated, and what are the prior probabilities of these markets? But before we do that, let us first understand the background of what is the Thompson lumber case. John Thompson is the founder and president of Thompson Lumber Company, a profitable firm located in Portland, Oregon. John's business challenges identifies whether to expand his product line by manufacturing and marketing a new product, which is a backyard storage sheds, and what are his alternatives. Thompson determines that there are only two possible outcomes. The market for the storage sheds could be favorable, meaning that there is a high demand for the product, or it could be unfavorable, meaning that there is a low demand for the sheds. This will now be the focus in this discussion. Through discussions with the experts, Thompson has learned the information in this table. He can use this information and Bayes' theorem to calculate posterior probabilities. To understand it better, let us have a quick review of the Bayes' theorem. Let us say there are two events, A and B. What is the probability that both of them happen? In one hand, you can start by looking at the probability of A in proportion to all the possibilities that A is true, and multiply that to the proportion of those events where B is also true, which is the probability of B given A. We can also think of it as the cases where B is true among all the possibilities times the proportion of the possibilities of those where A is also true, which is the probability of A given B. This may look the same, which can give us the expression of an A given B, or the other way around. When we put numbers into it, say, we're given a number of evidence against the number of hypotheses, then it becomes a powerful tool. In calculating the probabilities using the Bayes' theorem, let A represent the favorable market and B will represent a positive survey. If we will supply the given data into the formula, the favorable market where the survey results are positive is 0.78, and the unfavorable market where survey results are positive is 0.22. Here is the updated probability revisions given the positive survey or the posterior probability. A posterior probability in Bayesian statistics is the revised or updated probability of an event occurring after taking into consideration new information. In statistical terms, it is the probability of event A occurring given that event B has occurred. In this case, we are looking at a favorable market, both taking into consideration the promoters and the detractors. Here is the revised probabilities, this time considering the negative surveys. We can see in this table the negative surveys occurring in both a favorable market and unfavorable market. From here, we can see that there are more detractors in unfavorable market than with the favorable market. John Thompson's prior probability was limited to just two choices, a high demand or a low demand. In using Bayes' theorem, all market conditions was considered. We can create a simple formula for Bayes calculation using Excel. Considering that all your values are arranged in the same way as how it is being shown herein, you can enter the probability of a survey positive in a favorable market in cell B7 and the unfavorable market in cell B8. You can input the probability value of a favorable market in cell C7. To create the formula, you can subtract the value of Fm and Um from 1. Identify the prior probability value. Compute for the joint probability value. Then supply the information with the Bayes formula to arrive at your posterior probability. And here's the result of the Excel calculation that shows the posterior possibilities of John Thompson's choices against his prior probabilities. From having only two choices as the prior probability, Thompson Lumber now have a deeper look into the market, showing the promoters and the detractors from both the favorable and the unfavorable market. Applying the Bayesian analysis doesn't come without challenges. First, we cannot always get the necessary data for analysis. Second, survey results may be based on cases where an action was taken. And last, conditional probability information may not be as accurate as we would like.
Created using Powtoon.
Utility refers to the satisfaction that each choice provides to the decision maker. Thus, utility theory assumes that any decision is made on the basis of the utility maximization principle, according to which the best choice is the one that provides the highest satisfaction to the decision maker. Here's your decision tree for a lottery ticket. You have the option to accept and get $2 million or reject the offer with an EMV or expected monetary value of $2.5 million. Please note, however, that this is dependent on the outcome of the heads and tail as the game proceeds. You lose your money if heads and you double the amount if tails. The standard gamble presents choices between two alternatives, with the probability of each being varied until the individual is indifferent to the choices. In the diagram, whatever is your choice, you will always have the best outcome utility and the worst outcome utility, where the outcome of the unselected choice is unknown. Jane Dixon wants to construct a utility curve revealing her preference for money between $0 and $10,000. A utility curve plots the utility value versus the monetary value. An investment in a bank will result in $5,000. An investment in real estate will result in $0 or $10,000. Unless there is an 80% chance of getting $10,000 from the real estate deal, Jane would prefer to have her money in the bank. So if P is 0.80, Jane is indifferent between the bank or the real estate investment. A utility curve shows a combination of two possibilities that give an equal satisfaction in utility, thereby making the person indifferent. This is a plotted utility curve of Jane's investment options. Along the curve, she may have an equal preference for the combinations of investments shown, like she's indifferent about any combination of investments on the curve. Typically, indifference curves are shown convex to the origin and no two indifference curves ever intersect. Jane's utility curve is typical of a risk avoider. She gets less utility from greater risk. She avoids situations where high losses might occur. As monetary value increases, her utility curve increases at a slower rate. A risk seeker gets more utility from greater risk. As monetary value increases, the utility curve increases at a faster rate. Someone with the risk indifference will have a linear utility curve. Let us look at another example of utility as a decision-making criteria. Mark Simkin loves to gamble. He plays a game tossing thumbtacks in the air. If the thumbtack lands point up, Mark wins $10,000. If the thumbtack lands point down, Mark loses $10,000. Mark believes that there is a 45% chance the thumbtack will land point up. Should Mark play the game? We establish the utility curve of Mark Simkin by finding his utility values and replacing the monetary values with the utility values. His graph shows that he is a risk seeker. To answer the question, should Mark play? Mark have a higher utility at point 30 that the thumbtack will land point up. Note that utility is defined as the highest satisfaction to the decision maker. Therefore, Mark should play.
Created using Powtoon.